Welcome! In this mini-lecture, we're going to cover the key idea of section 12.1, functions. So we're going to begin by formalizing what it means to be a function. So we're going to suppose that we have a and b that are sets, and we will define a function f from a to b to be a relation from a to b. And so f is a subset of a cross b. And that relation must satisfy the property that for each a in A, the relation f contains exactly one ordered pair of the form AB. And we usually denote that as f of A equals B. That's the common function notation that you're familiar with. And this definition jives with what you've learned about functions, that they satisfy the vertical line test. That's the exactly one ordered pair part of the definition. So, for any function f from a to b, the set A is called the domain of f. And so A is the set of inputs for our function. The set B is called the codomain, and this is the set of possible outputs. And that word possible is important, because not everything in the codomain has to be used. So this is the set of possible outputs. And we're going to call the range of f the set of what actually comes from our input. So it's the set of actual outputs. So if we think about a common function, let's consider, say, the function f, which maps the real numbers to the real numbers, defined by f of x equals x squared. Well, in this case, we know the graph looks like this. So we know it is a function. It's going to satisfy that vertical line test. We can see that the domain is the real numbers, everything on the x-axis. The codomain is also the real numbers, but not all of the real numbers are used. So the codomain in this case is the real numbers, but the range is actually the positive real numbers together with 0. So that's the difference between the codomain and the range. Lastly, we will say that two functions, f, which maps a to b, and g, that maps c to d, are equal if a is equal to c, b is equal to d, and f of x equals g of x for every x in the domain. So the domains have to be the same, as well as the codomains have to be the same. And then all the outputs have to agree. Those are the three things you need to check. So, again, if two sets are equal, we need to check that their domains, codomains are the same. The domains are the same, the codomains are the same, and all the outputs agree. So, if you take a moment and think about functions that you know, I'm sure you can generate a large list. So we've already talked about, say, the function which maps the real numbers to the real numbers given by x squared. We could also consider x cubed. We might be able to think about, say, the square root of x. We can generate lots of polynomials and things like that. So let's try to dream up something that might be a little bit more interesting. Perhaps we might consider, say, the function that maps -4 to 4 onto the real numbers, defined by, say, f of x equals the square root of 16 minus x squared. So here, our codomain is the real numbers. Our range, what would our range be in this case? Think about it a moment. Our range would be from 0 to 4. If we think about the graph of this, it would be a half circle. So again, that's kind of similar to what we were just thinking about. Could we take it one step further? How about considering, say, a function that maps negative pi over 2 to pi over 2 onto the real numbers, and we can define it by, say, tangent of x. So in this case, the codomain is the real numbers, as well as the range is the real numbers. And so you might consider thinking about the trigonometric functions, exponential functions. There's lots of ones that we know. So now let's take and consider another one. We want to know here, is f a function? It's mapping xy as y equals x squared minus 4 over x minus 2. Your gut reaction might be, yes, of course that's a function. We can have rational functions. But if we think a little bit harder, this is not a function. Why is it not a function? At x equal 2, the function is undefined. So it would not produce any output. So in this case, it's not a function. If we wanted to make it a function, we could amend f to say be the ordered pairs x, y that are elements of R. 2 is the only problematic element we have. So if we take 2 out of our domain, then this would work as a function. So make sure that you pay attention to your domain when you're asked to decide if something is a function. Let's consider another one. Is g a function? Where g is defined on the natural numbers cross the natural numbers, where the relation is x is less than or equal to y. So when considering g, defined on the natural numbers cross the natural numbers with x less than or equal to y, we see that this is not a function because there are many pairs such as 1, 2, 1, 3, 1, 4, where we have the same input but many different outputs. So this is not a function. So how might we change this to be able to make it a function? If we change that to be an equals instead, then it would become a function. So now let's look at an example where we want to show that two functions are equal. So we're going to have f defined from a to the real numbers, being defined by f of x equals x cubed minus 9x squared plus 23x minus 12. And a is the set 1, 3, 6. We're going to let g be mapping b to the real numbers and being defined by g of x equals x squared minus 4x plus 6, where b is the set of natural numbers that divide 6, and taking out the numbers where x is an even prime number. So the set b, as stated, seems a little cumbersome. So let's see if we can think about what would the set b look like. So the numbers that divide 6 are 1, 2, 3, and 6. Now, if it's an even prime number, that's 2, so we need to take that out of our set. So ultimately, we see that b is in fact the set 1, 3, and 6 as well. So to prove that two functions are equal, the first thing we need to do is check that our domains and codomains are the same. The domains A and B are equal, so that's good. The codomains are also equal, note that they are both the real numbers. So the domains are the same. The codomains are also the same. That was the first thing we need to check. The next thing we need to check is that every value agrees. So we need to check f of 1, f of 3, f of 6, and compare with g of 1, g of 3, and g of 6. If we substitute our values in, if we substitute in 1, we see that we get 3, 3, and 18 and when we substitute into f. When we substitute 1, 3, and 6 into g, we find that we also get 3, 3, and 18. Because these are matching for every value in our domain, we see that the functions will in fact be equal. So when we are proving that two functions are equal, we need to check their domains are the same, we need to check that the codomains are the same, and that they agree on every value. In this case, that was easy to do because there were only 3 values. In many cases, you'll need to do some algebra. So that's all for now. Thanks for listening. Have a great day.